still have 1 minute. Okay, let's begin. So this is my customary lecture summary. I have, this is beginning of week 13, and I put here what I had started to do since the beginning of the semester for those of you who are interested. This is an NPR program about the 50 great teachers, and the first one was Socrates, the ancient world's teaching superstar. And so Socrates says that you should teach by questioning, and I say you should also learn by questioning. That's what we have been doing since the beginning. And this is a very funny video, 5-minute university, and which I also learned from this Harvard professor, Eric Mazur. So I leave that for you to read, except that in this week here, I won't be able to do as much interaction as I wish to, because I would like to coach the class on the exam problems and also on the report problems, okay? And show to you the connection between what we did with Fourier series and what you would do in problem 5.1 and in the exam problem, exam 2.1 problem 1, regarding projecting a function on the polynomial basis, but defined on an interval that is not from 0 to 1. Okay? So that you can see that everything you learn are connected together. They are not separated topics. They are all tightly connected. Okay. So let me begin by going back to Theme 6. Problem 4.5, which I had discussed before, except that I just look at this and I'm a bit disappointed that the result of the integration was given, but the details of the integration was not provided. And so I really want the class to be able to carry out this integration. And it's not just for the exam, but also just for the intellectual understanding, right? How you would do this integration, and also allow you to check with the results. I don't know what Team 6 use as a tool to obtain the results, but like I said, I won't be able to really interact as much as I wish to. So I just provide the information, but I wish that, I hope that if you have something that you'd like to ask, do feel free to do so, okay? I will be happy to answer. In fact, I like interaction. So if you have questions, do ask. I want to show to you some important trigonometric identities that you need to know, and that would be useful for your exam. Okay, and I talked to several students, and by observing students how they learn, I noticed that students learn when there's homework to be due and exam to be done, and so that's how things are going. This is meeting. I need to prepare my handwritten notes here. Let's see. Oh yeah, I can use this one, and I can. The last time, meeting 41, I did not write anything, so I can change the file name to meeting 42. Okay, so normally I would ask the class to contribute and getting active learning credit, but now I just want to really make sure that you know this. I think there are two important identities that we want to remember, okay? And these are not I even provide the identities in my exam statement. But this is what you want to remember, cosine. Okay, cosine of A, B equal to cosine A, cosine B. I leave a blank space because I will come back. And by the way, I had begun to review for the exam long before today. Okay, so please keep that in mind. So first, begin with a plus sign. Then you want to remember that on the other side, that's the minus sign. Okay, and when you have a minus sign, then on the other side you have a plus sign. All right, so this is a very important relation, and from where you can rederive all of the other relations. For example, if you want to carry out the integration honestly, not just put the result, you see that here is a product of two cosines, right? Two cosines. So how okay, you see, if you read carefully, team 6 write ij here, right? But this result here, when it's not equal to 0, I must be equal to j, and they wrote over here. So be careful reading these reports. Down here, they also had I and j, but they did write over here I different from j. Okay, so keep that in mind. What I want to show to you quickly is that if you need to integrate, so that integration is integrating from 0 to 1 of cosine. Let me use n, right? Just to be sure here, n, right? Okay. Yeah, this is note that L is 1, okay? And because as written here, you see. And I will come back to this formula. When I concocted this problem, in fact, what you are doing here is an even a half period, even half period extension of the logarithm. Okay. So that means that. So let me explain here. The logarithm is given only on an interval. So a half period or even half period extension. So you can think of this as a half period, and an even extension is when you complete the other side into an even function. So it would go from -1 to +1. Okay, so and then think of this as repeated periodically, right? From -infinity to +infinity. So and pay attention to this formula. It's from 0 to 1, and I will connect this to the formula for the coefficients of the Fourier series that goes from -L to +L, and then you can see why here you integrate only from 0 to L. Okay, so in this note here, suppose that if L is not 1, then the integral should be from 0 to L of m omega, which is pi over L, right? So you have this, and then multiply by cosine of n pi x over L dx. Okay. So you want to convert the product of cosine into a sum, right? So that you can integrate. So the trick here is that you can split this equation here into two different expression. So let me just copy down here. Okay, and also copy down here and remove the blue sign on top and remove the red sign at the bottom equation. Okay, and so you can see that if you add these two expressions, you can get rid of the product of the sign, and therefore what you have would be the product of the cosine, right? Add this one to this one, so therefore you have 2 times cosine A times cosine B equal to cosine of A plus B plus sine of plus cosine of A minus B. Okay, so therefore, and that's what you want to use. So let me write down here cosine A cosine B will be equal to 1/2 of cosine of A plus B plus cosine of A minus B. And then once you convert the product of cosine into the sum of 2 cosines, you can integrate this easily, right? So that's the method. Okay. Let me not carrying out the details unless someone needs. Okay. So once you apply this to this integral here, the integration should be easy. Okay. So that's what you want to keep in mind. And so to do the work completely. So now let me coach you immediately in well before the review. Okay, so and this is in exam 2.2 problem 4. So exam 2.2 problem 4 right here. I did not write on the formula. Right. I gave you the formula here, so you don't have to memorize. And I give you the function is cosine square. Okay. So I ask you to expand into Fourier series, and I give you a hint: transform cosine or sine using a formula given above, meaning this one. Okay, transform the function cosine square into cosine or sine using that formula. So the method would be, cosine square would be just cosine times cosine, right? So now instead of cosine A times cosine B, you just set A equal B, so then you have cosine A squared. Okay, so that's what this hint was given to you. Okay, so let me write down here. Right, so now you think of A equal B, right? So if A is equal to B, then, and look at only the formula with the plus sign, right? If A equal to B, this is cosine 2A, and then you have cosine A squared, and this would be sine A squared, right? So therefore, you have from this formula, let me rewrite here so that you can see where it came from. And you set A equal to B, then you have cosine 2A equal to cosine A squared minus sine A squared, right? But you want to express cosine A squared in terms of cosine or sine, right? The next step is to remember that sine squared can be written as 1 minus cosine squared A. Okay, so minus minus becomes plus, and therefore over here you have right 2 cosine square A minus 1. Okay. Now you can solve. Let me move down here. So you can now express cosine square in terms of cosine of 2a. So therefore, cosine square of a is equal to 1 plus cosine 2a divided by 2. Okay. Or you can write as follows: 1 over 2 plus 1 over 2 cosine of 2a. Okay. So this cosine square a has a constant term plus a term that has cosine 2a. It's already the Fourier series, just by doing trigonometric manipulation. But still, you need to justify that this is a Fourier series. Okay. Meaning that without computing, you know, for example here, if you the function f of x is cosine square a, right, or x. Okay. So therefore, by the result that I just derived, you can write as 1/2 plus cosine, or 1/2 here, also 2x. Okay. But if you use the formula for Fourier series, you see that this would be equal to a0 plus the sum of an cosine of n omega x plus the sum, let me write the sum down here, bn sine n omega x. Okay. Right, and a0 is a constant. Okay, and that was that's 1 over p. Remember, integral from 0 to p. There are two formulas that you can use. Maybe let me give you the formula that you would see in the book first, and then show you the other formula that is equivalent. Okay, so this would go from minus L to L of fx dx. Okay, and you can replace p by 2L. Okay, so p is equal to 2L. Let me move over here. Okay. Then at least if you use this formula, you can integrate, right? Because fx is cosine square, and I showed you at the beginning you can convert cosine square into the sum of. In fact, it's right here. You can convert into this one, right? Into sine or cosine. And so you can clearly integrate this one. Okay. Now the next one would be an equal to 2 over p, which is 1 over L, integral from minus L to L, right, of f of x times cosine of n omega x. Okay. Dx. Okay, so what is omega? If you look at this, let me clear the ink. Okay, so this is a cosine function, right? And so the period would be the cosine function. The period of cosine is 2 pi. Okay, but you need to square it up. So essentially, it looks something like this, right? You have cosine of 0 is 1, so this would be 1 period. 0 here, okay, and the other place would be pi here, right? And this is pi over 2. Okay, let's see. Yeah, minus 1 is right here, plus 1 here. Okay, and over here you have minus pi over 2. Or you can go up to here. Okay, so this is would be 3 pi over 2 and 2 pi. Right? So so when you square up, you know, the negative part would become positive. Okay, so it would look something like that, and so therefore the period would be reduced to pi. Okay, so p would be equal to pi for the cosine square. All right, and so omega is 2 pi over p, so therefore omega is equal to 2. All right, so let me write down over here. For cosine square, period is equal to pi, and therefore omega is 2 pi over p is equal to 2. Okay. So in that case, an is equal to 1 over L, integral from minus L to L, and you know that L, this is equal to 2L, so therefore L is equal to pi over 2. That's half the period. And you need to integrate cosine square of x, right? And then cosine of nx, because and n2 times nx. Okay. dx. Now this how do you integrate this? Well, you can convert cosine square into 1 plus 1/2 of 1 plus cosine of 2x, right? And then you can multiply out, okay? And then you have another product of cosine and times cosine, and then you have to keep doing that. You know, convert the product of 2 cosine into the sum of 2 cosines, right? Then you can integrate. Okay. But you can also use orthogonality in the following sense. Okay, you know that 1 is orthogonal to cosine of 2nx, okay, over 1 period, because the Fourier basis functions are orthogonal to each other. You need to say that. Otherwise, you need to carry out the integration. And second, cosine of 2x is a particular case of cosine of 2nx with n equal to 1. Right? So for n equal to 1, you get cosine of 2x. So for n greater than 1, cosine of 2x is orthogonal to cosine of 2nx. Okay, meaning that the product, if you carry out the integration, will be 0. For n greater than 1. Okay. And so therefore for n greater than 1, you have an equal to 0, right, due to orthogonality. So meaning the integral of from minus L to L of 1 times this is 0, okay, and this is for n greater than or equal to 1, because for n equal to 1 that works also. But the next one, cosine of 2x times cosine of 2nx, dx would be 0 for n greater than 1. Okay. So that's the reason why this coefficient will be 0 for n greater than 1, and for n equal to 1, you get exactly this one. Okay, this is the coefficient for n equal to 1 here. That's 1/2. Or you can also carry out the integration, right? For n equal to 1, you just need to, let me rewrite this expression here just by copying and write it down here. Okay. For n equal to 1. Okay. You can replace as A1, right? And that would be this one. Okay. So in principle, you can carry out the integration, and the result should be equal to 1/2. Okay, based on the trigonometric identity. All right. And you can do the same for Bn. You can show that Bn is 1 over L, integral from minus L to L of fx, that's cosine square, times sine of 2nx dx. Okay. And you can use orthogonality. Once you convert cosine square to 1/2 of 1 plus cosine 2x, then you can appeal to orthogonality, because 1 would be orthogonal to sine of 2n for any value of n greater than or equal to 1, as well as cosine of 2x is orthogonal to sine of 2nx for all n, okay, greater than or equal to 1. You can verify that by carrying out the integration. So all of these Bn here would be equal to 0, okay, for n greater than or equal to 1. The point is that just by doing trigonometry, as shown up here, right, to convert cosine square into cosine, you already get immediately the Fourier series. Okay, the rest is just to verify that the coefficients are indeed, the constant would be 1/2, and the coefficient A1 here, this is A1, would be also 1/2. Okay, so let me note down here for you. This is A1. Okay. And the shortest way to do this is to appeal to orthogonality. as a known fact. Okay. And so once this step is done, then the rest would be simple. Okay, the rest would be just I gave you, for example, this is a linear second order ODE, a simple one without damping. Okay, and these are the initial conditions. The particular solution, because cosine square is 1/2 of 1 plus cosine of 2x. Then you know how to find the particular solution of this one, right? Because you can split this sum here into a constant and a cosine. For a constant, you know how to find the particular solution. Okay, make sure you do. And for the cosine, the trial particular solution is again sine of 2x, or a times cosine of 2x plus b times sine of 2x. And you need to replace that into the equation. So we have two equations and two unknowns to solve for the coefficient a and b. Okay. This is a review of the differential equation, and you also need to look at my section 7. Okay, to review. The homogeneous solution is simple, and then once you have the particular solution and the homogeneous solution, you can satisfy the initial condition, and once you obtain the complete solution, you can verify that the solution was correct by replacing into the differential equation. Okay. Any questions on this? Be sure to know how to find a particular solution. All right. Okay. So that is already, doing the whole problem for a half of time there. Okay. So now let me go back to my daily lecture summary here. All right. Now I'd like to address 5.1. So what I need for you, in fact, this would be, right here is problem 4. Okay, so I have already shown to you how to do problem 4. So this is done. Okay, now what I want to do before I come back to Fourier series is to show to you the connection between Fourier series and problem 5.1 and 5.1 here is to ask you to do projection on an interval that is not between 0 and 1, okay? But you want to take advantage of the Hilbert matrix, right? You want to take advantage of the Hilbert matrix, and the Hilbert matrix is only when you do the projection on the interval from 0 to 1. So the method is very similar to Fourier series. Remember when I showed to you in the last lecture, when you have the square wave that is arbitrarily placed in the 2D space, the method is to transform the coordinates so that the square wave sits like an odd function, right? Once you have the square wave as an odd function over a period, and expand into Fourier series, you would have what? Is it a sine series or cosine series? It's a sine series, because the sine function is odd. Normally, like I said, I would prefer active learning credit, but now I'm accelerating here. So, but please do think along with me. Okay. So once you obtain the Fourier series in the new coordinates, then you would transform back to the old coordinate system, and that's it. We have the Fourier series of a square wave arbitrarily placed in 2D space. Now for the projection here, it's very similar in terms of the thought process. The thought process is to transform the coordinates from something that is not from 0 to 1 into something that is from 0 to 1. Then do the projection with the new function in the new coordinates. Okay? Actually, let's look at the problem statement. The problem statement is problem 1 of exam 2.1. Okay, so let me bring up exam 2.1. Here I provide it to you, and let me put on the mask so that it's more focused. You see, in fact, I provided to you here the flowchart, the step-by-step procedure, right? Question 1, find the appropriate coordinate transformation from x to x bar that take advantage of the Hilbert matrix. That means that implicitly you want to know that I wanted to ask you, how do you take advantage of the Hilbert matrix? Do the transformation of coordinates such that x bar would be defined on the interval 0 to 1, right? Because that's how the Hilbert matrix can be obtained easily. Okay? If you work on an arbitrary interval, you don't get the Hilbert matrix. So, and then let's look at different questions first, all the questions, and then we'll go back and see how you do what. Second question, set up the projection equations in the x bar space. I already tell you, do the projection within the new coordinate system. Question 3, solve the projection equations and give the expression for the parabola. Well, you know that parabola means what? Polynomial of second order, right? Okay, ax squared plus bx plus c. Right? So polynomial second order. So meaning that essentially I ask you to approximate the exponential function by a polynomial of second order. Right? And you can do the projection in the x bar space. That means that the Hilbert matrix, you no longer need to compute because you know the formula for the Hilbert space. Okay. And so therefore you only need to compute the right hand side. Okay. And in this problem here you have 3 unknown coefficients because the parabola is a second order polynomial. You have 3 coefficients. So it's a 3 by 3 matrix. Okay. And the 3 by 3 Hilbert matrix, you know, one half, 1/3, and so on and so forth. Okay. And all of you have the SAT calculator, and the SAT calculator can solve linear system, right? Simultaneous equations, right? Okay. Otherwise, you can also write in your formula sheet the explicit inverse of the Hilbert matrix. It's also very nice. It's very neat. You can use Wolfram alpha, and it gets to you the expression of the inverse. Okay. Anyone who has a calculator that cannot solve linear system, simultaneous system, I think everyone would have that. So this should not be a problem. And then after that, once you obtain the projection, meaning the approximation of the exponential function in the x bar space, then you can just transform x bar back to x, right? That's the question 4. Just like in Fourier series. Okay, so these are the steps that you need to do for this problem and for the report problem 5.1. Okay, so now how do you find that coordinate transformation? And actually, it's very simple. For example, x goes from -2 to 4, and you want a new function, a new coordinate x bar that goes from 0 to 1, right? So let me go to a new page. the best way to explain is through a picture, because a picture is worth 1,000 words. So this is my coordinate system. Okay. Think of the horizontal axis as the x-axis. And think of the vertical axis as x bar, which is basically a function of x. Okay. So you can write x bar as a function of x like this. Or if you are not comfortable with this notation, you can think of it like this. I avoid to use f because f is already the exponential function. Okay. So and note that x in the problem statement goes from -2. So let's 1, 2 to 4. 1, 2, 3, 4. Right? And you want, and now let me not use the same scale in the vertical direction, so I can exaggerate the graph. So let me, okay, so this is -2 and this is 4, whereas this is 1 in the vertical scale. Okay, so that I can have a bigger, so here, so the first point, right, the first point would be 0 and -2, so it's right here. That's the first point. Right here, right, the coordinate, and the second point would be have the coordinate 4 and 1. Okay, so 4 and 1. Like that. And so this is the second point here. And so what you want is a straight line that goes from this point to this point. Okay. So you see that if you take any point x, right, I can write x here between the interval from -2 to 4, then this linear map would map this point to a point x bar between 0 and 1, right? So that's what you want. It's real simple. So let me draw that. Okay, maybe let me do like this. So that's a mapping from x to x bar. All right. So what is this? So the function g that you want to find is just the function of a straight line. Okay. So you can write as follows. Maybe you can write like this. You know, x bar is equal to g of x, yeah, equal to alpha plus beta x. Okay, so that's a straight line with two unknowns, alpha and beta, and the two equations for these two unknowns is just by putting in the coordinates of these 2 points, right? So this would be here x is equal to -2, x bar is equal to 0, and at this point x is equal to 4 and x bar equal to 1. Okay, so then the first point with x equal to -2, x bar equal to 0, then you get the first equation, right? And then for the second point, x equal to 4 and x bar equal to 1, you get the second equation that you can use to solve for alpha and beta. Thank you. Okay? I don't think I need to go deeper into this, right? This should be that you should be able to do this. Okay, and once you have this, then you can express x in terms of x bar, right? So x would be simply x bar 1 over beta of x bar minus alpha. Okay, and f of x is let me go to the exam statement here. 2 times exponential of x divided by 4. So then you can write as 2 times exponential of 1 over 4 of this one. Or I can even write directly 4 beta x bar minus alpha. Okay. Right? So this is a new function. It's like as if you are given this function with x bar between 0 and 1, you apply the known method in one of my lecture notes, working only on the interval 0 to 1. The Hilbert matrix is given, and therefore you don't need to construct the Hilbert matrix. You only need to find out the right-hand side. Okay, let's solve for the coefficients, the 3 coefficients of the parabola. And then once you obtain the 3 coefficients of the parabola, that is in the x bar space, then you would use this relation here, because x bar is alpha plus beta x, so that you can convert back to the x space. Okay, so that's the solution of the problem for both problem 5.1 and for the exam problem 2, exam 2.1, problem 1. Okay, so lecture summary.